Okay, so we're going to go ahead and we're going to start the class. And I guess I'm going to start out by asking if anybody has any questions at all.
I have a quick question.
Sure.
Is the multidimensional rectangle function just it's from -1/2 to 1/2 on every dimension?
If you have a rect function, you know, that's that capital pi. If you have pi of t1 times pi of t2, yeah, it goes from -1/2 to 1/2 in both dimensions. And you'll notice it's still kind of cool because it still has an area now of 1, doesn't it? Just like the one-dimensional case does. So it still has an area of 1. So yes, that's true. Okay, hearing no more, let's talk about the homework a little bit. So I am going to share my screen. And now you should all see my screen, and we are going to, before we do this, I want to tell you about a book I just wrote. And I hope if you're interested, you buy it. It's for a greater purpose, the life and legacy of Walter Bradley. Some of you may or may not know Walter Bradley. He was a professor. He's a distinguished professor emeritus here at Baylor. He was responsible for me coming to Baylor and has lived one of the most outstanding lives of any man that I've ever known. I made a list one time of all the people in my lives that were kind of my heroes that had a major impact on my life, and Walter Bradley is definitely near the top of that list. If you want to read a great book, you should read this. One of the cool things is you might know some of these people. You might have heard of Douglas Axe. He says, luminaries like Walter Bradley paved the way for me to dedicate my career to advancing design thinking in biology. He had effects on people of all different walks of life. He was one of the first people to found with his wife Anne a crisis pregnancy center in College Station when that became a situation. But he led a very solid Christian life. John Burke, pastor of Gateway Church. If you want to read a fascinating book, read Imagine Heaven. Imagine Heaven is the book about near-death experiences. And many of you know William Lane Craig. How many have heard of William Lane Craig? I think probably a lot of you have. He's one of the premier apologists today. He's a philosopher and a biblical scholar, and heads Reasonable Faith. And he worked with Walter Bradley. In fact, William Lane Craig stayed over at Walter Bradley's house a bunch of times. And he says Walter Bradley is one of the most extraordinary men I have ever known. I am in awe of him. And to figure out why William Lane Craig is in awe of Walter Bradley, you might want to read the book. Some of you know David Jack. He's a professor here in mechanical engineering. He says the influence of Walter and Anne on my life cannot be measured. Some of you know Jay Richards, who is the co-author with Guillermo Gonzalez of the Privileged Planet. Says Walter Bradley woke me from my dogmatic slumber. So this was an impression that he made on Jay Richards in terms of his academic pursuits. And how many have heard of Hugh Ross? Hugh Ross is a great apologist, and in fact, many of my original books on apologetics were from Hugh Ross. He is a great man. He says, one of the great blessings God has granted me in my life is the opportunity to have co-ministered with Walter Bradley among faculty and students on university campuses in the U.S. and beyond. Anybody know who Robert Sloan is? He was the former president of Baylor University. 2 presidents back. He left and he's now the president of Houston Baptist. So he was here when Walter Bradley was a professor here, and says Walter Bradley is one of the most remarkable Christian scholars I've ever known. How many know Professor Thomas? Okay, if you've been here as an undergraduate, you know Professor Thomas. He is the master at what's the residential college?
Teal.
Teal, yeah, he's the master at Teal, and Walter Bradley got Professor Thomas interested in appropriate technology, which is a great ministry. It's the idea that we who are technical don't need to maybe bring the latest, biggest computer to developing countries, that there's other ways that we can help them. We can help them with technology that is appropriate for them. So Professor Thomas has imitated Dr. Bradley, who has gone to developing countries and help the natives using their own resources find their own business, and then let the nationals take over the businesses and develop a thriving entrepreneur visit. James Tour is just incredible. He should have been nominated for a Nobel Prize because of his work in micromolecules. And he said, Professor Bradley fearlessly led the charge for faculty to unabashedly stand up for their faith on campus. So anyway, if you want to read a good book, it's there it is, For a Greater Purpose. The Life and Legacy of Walter Bradley. It's by me, William Dembski. And the foreword is by J.P. Moreland. How many have heard of J.P. Moreland? He is one of the most premier Christian philosophers in the world today. He's a professor at Biola and has written some great things. Okay, so I thought I'd start that out with an advertisement. If you want to read a good book, it's available in Kindle, paperback, and about a month is going to come out in an audio version. If you're like me, if you're like me, I like Audible sort of thing. So yeah, it is coming out in an Audible version very soon. Okay. So with that, then let's go to the homework, and let's see. I suspect, but don't know for sure, that you have not looked at this. So let me go through these and see if you have any questions on them, because I'd like to know that at least you have a handle on attacking what these problems is. So let's go to 32 first. What is the Fourier transform of the sinc times the rectangle function times e to the minus pi t3 squared? Now this is clearly a three-dimensional signal, right? It's a three-dimensional signal. So can anybody volunteer what tool that we've used thus far to attack this problem?
Separability.
Separability theorem, right? It's the product of three one-dimensional functions. So that should get you going. Here's a trickier one. What if you have a two-dimensional function that is just a rectangle function? Remember, we said that a one-dimensional function was equal to, well, on the plane, on the T2 plane, it's like taking the one-dimensional function and smearing it along the axis that isn't represented in the function. So this would be a rectangle function smeared along the T2 axis and would appear as a slab in 2 dimensions, right? A little step up, a little step down, if you're going from left to right. So what's the Fourier transform of this? How would you analyze this?
I have a picture. I can show you what I think it's like.
Okay. Okay, let's stop sharing and
it's like sorry. It's like a sink in 3 dimensions. Like
nope, that's wrong.
No?
Nope. Nice try though.
Okay.
Yeah, that's a good try. It would be a sink, but it's a little bit different. Okay, David.
A sink times a delta, direct delta.
You're right, because notice we can apply the separability function or the separability theorem here. This is x of t1. What is the function of t2? The function of t2 is 1, right? So we're multiplying pi of t1 by 1. So therefore, if we Fourier transform the big pi, we get a sinc. If we Fourier transform the 1, we get a what? A delta function. And so I like Glauco's idea. So we're gonna use this. I'm gonna do sketch it. And here is another one. What is the Fourier transform? Now, it turns out in Google Docs, they don't have a vector. And their math stuff is not the best in the world. So when there's a vector, I try to put a line over it. But even there, it's inconsistent. And I haven't taken the time or effort to figure out. Sometimes it puts the line way above the variable. Sometimes it puts it right on top. So I'd like you to just, I'd like you to evaluate this, and then let's do this. Let's also do a sketch it. I like that. Sketch it. Now remember, in one dimension, this we're on problem 35 here. Remember, if we're in one dimension, that the Fourier transform was Hermitian or conjugately symmetric. I think conjugately symmetric is probably a better description, because Hermitian, you got to go to a dictionary or something to figure out what Hermitian is. But conjugately symmetric means in one dimension, if you Fourier transform a real function, if you have the Fourier transform, you switch it around and you conjugate it, you get the same thing. Do you remember that property in the one dimensions? This extends to multi-dimensions, and I'd like you to show this, that x of u, that any Fourier transform of a real function, notice x of t is real, that the Fourier transform obeys this conjugate symmetric relationship. Now what this means physically is that you take the function big X, you flip it around in all of the axes. You take T1, you make it into minus T1. You take T2, you make it to minus T2. If you have T3, you take T3 and make it into minus T3. And then once you've done all that flipping, you conjugate it. And if the original signal is real, you'll get exactly the same thing for its Fourier transform. So this is the way that the symmetry of the one-dimensional function manifests itself in higher dimensions. The math is exactly the same. The interpretation is a little bit different, but I'd like you to show this, and it's not difficult to do at all. Then the next thing I'd like you to do is I'd like you to figure out the Fourier transform of this function. And I tell you what I'm looking for. The little trick here is to take the cosine and expand it via Euler's formula into an e to the j plus an e to the minus j. Does that make sense? You're familiar with Euler's formula, right? No? Ooh, okay. Euler's formula. Euler's formula. In fact, I know we talked about this before. Euler's formula says that the cosine of theta is equal to 1/2 e to the j theta plus e to the minus j theta. That's Euler's formula. Euler is probably unarguably the greatest mathematician that ever lived. He was just astonishing with his output, just astonishing. And he had a number of papers scheduled to be published after he died, like 100 different papers, because as he got older and older, his eyesight began to fail. And he was the consummate nerd because he lost his sight in one eye. And he was a Christian, it turned out. And he said, I thank God for this, because now I have, I will be less distracted from my mathematics, because he only had one eye. His other eye would distract him from his mathematics. But then he lost the sight in his other eye. And if you've ever seen pictures of Euler, you can see he has kind of a weird eyeball. Let's see if I can find one here. Euler. He spent most of his time in where did he spend his time? In St. Petersburg. Yeah, but here, for example, you can see, can you see his eye?
We still see the whiteboard.
Oh, you still see the whiteboard? Okay, thank you. Okay, is that okay? I think you can see the picture on the right is of Leonard Euler. And can you kind of tell something's funky going on with his eyeball? this is one of the cases where he had lost his probably lost the sight in one eye, and before he lost the sight in his other eye. But even when he went blind, he had a bunch of people, since he was kind of sponsored. I think it was Frederick the Great, not sure. No, not Frederick the Great. Who was the head honcho in St. Petersburg in Russia? Okay, you guys don't know your history either. But he was sponsored. He had a bunch of mathematician kind of interns that sat around the table, and he would sit around and he would explain his ideas to his intern, even though he was blind. And this resulted in the accumulation of like 100 papers that were published even after his death, because all of his interns had all these papers. But the things that he has named after him are just really, really incredible. In fact, some people say that E, like from e to the x, is named after Euler, but it isn't. Okay, Euler Theorems, Wikipedia. Okay, I'm not getting it. But you've probably heard about a lot of these. Here we go. Things named after Euler. There he is with his bum eye. But I want you to look at this. These were his conjectures, his equations. He actually did stuff in industrial engineering. And it just goes on and on and on. So you believe Euler was a smart guy? These are just things named after him. And notice they're not single column here, they're double column. So he's a pretty impressive guy. So anyway, let me stop sharing and then go back to the screen. And I know that we covered Euler's problem here before, and I'll tell you what you could remember. Can you see my screen now? Remember, we said that the sine of theta is equal to 1 over J2. Whoops. E to the J minus e to the minus J. And I know we covered this because when we covered even and odd problems, I said, what is this is a function, and this function has an even part and an odd part, right? Do you remember that? And this was the even part, and this was the odd part. And so those are Euler's functions. And if we combine those, notice if we add these two, we get this is equal to cosine of theta plus J sine theta. And the reason we love this is because in engineering, we have the complex plane, right? And do you guys remember what the magnitude of e to the J theta is?
Cosine of theta?
No.
1.
Yes. Now, Aiden, you're right. The real part of e to the J theta is equal to cosine. But here's, the actual magnitude of e to the J theta is 1. And what we do, and you can do this because the magnitude of e to the J theta, let's do it squared, is equal to the real part squared plus the imaginary part squared, which we all know adds up to 1, right? So we always conclude this formula as e to the J theta, which is a point on the complex plane, is 1 at an angle of theta. Why is that? It's because the real part here, this dimension, is equal to the cosine of theta. And this dimension here is equal to the sine of theta. And of course, since this is the imaginary axis, we usually put a j sine of theta here. So, so that's the beautiful relationship between e to the j theta. And so when I teach the course where I introduce complex numbers, e to the j theta cannot be thought of as 2.7. I don't even know what e is anymore, raised to the square root of -1 times theta, right? That's a stupid way to think of it. You have to think of it geometrically into these terms. Okay, so this being the case, let's go back to the problem that we talked about. Okay, where'd you go? Where'd you go? Where'd you go? There we go. Nope. Oh yeah, here we go. Okay. So when we're here, what I'd like you to do is to take this cosine theta and divide it into 1/2 e to the j plus e to the minus j. Can anybody see the advantage of doing that? What happens when you multiply a function in by an e to the j phase t? What happens in the frequency domain?
Shifts.
It shifts, doesn't it? So the point is that the two functions of x of t we have here are the sinc and the cosine. And we can, because of the separability theorem, we can separate them. And we can get the sinc, okay, the sinc times e to the plus j, that's going to Fourier transform to the rectangle function shifted one way. And then the sinc times e to the plus j, that's going to give you a rectangle function in the frequency domain shifted the other way, right? So that's the quick way to do that. If you have a more simple way to do that, that's fine. You know, this is a technique that we can do. So I'd like you to look over these and work them out for next time, and we will talk about them. Any questions at all?
Dr. Marks,
Yes.
on 34, I missed what you said about that one, but I was wondering, can you not apply the rule of separability because it's just one rectangle function of like two different variables?
You know, you're exactly right. In fact, I was kind of remiss here because I haven't defined pi of t. Let's see, okay. I hate when I get inside the parentheses here. They don't even like that, okay. Let's try here. Because I haven't even defined this function, have I? Man, this is why I like LaTeX. Google Docs and Word thinks it's smarter than you are. And plus, they're different. Oh, gosh. Oh, how frustrating. Okay, well, how do you get up there? Okay, I won't even do that. Okay.
You hit the right key.
Okay, help me out so I can learn here. Okay, so I go pi of t 1. I hit what now? The right key.
Yeah, the right key. The
Which-
arrow right. And it'll move the cursor up.
Okay. Okay. I don't think it did what I wanted to, but that's okay.
Yeah, because I think you accidentally put a space before the 1 or something.
Okay, I'm going to do this, and then I'm going to go back and put in the subscripts. Whew, okay. LaTeX is a lot easier. I was taken to task because I'm mispronouncing LaTeX. Is it LaTeX? If has any of you noticed there is a food truck down by the what do they call that? The towers downtown.
By the bridge?
Yeah, the what?
The suspension bridge?
Yeah, by the suspension bridge. There's a little taco stand there called LaTeX.
Yeah, I saw that, and my roommate, he's a mechanical engineer. We laugh about it every time.
Did you? Have you ever eaten there at all at LaTeX?
No, I haven't ever tried it.
LaTeX is also something like spandex, right? Or I don't know. Okay, so this is, I didn't define what pi as a function of the variable is. So I have defined it over here. What does we see this notation a lot in mathematics. What does the colon equals mean? I think I mentioned it in here.
Yeah, that it's, this is the definition of what's on the left.
Is equal to by definition. Yes, okay.
What is the difference between colon equals and the triple bar equals?
I think they're the same notation depending on what school you were educated at. So I've seen that notation too, Adam. I've seen, like, instead of 2 bars in the equals, I've seen 3 bars. And I believe that's the same as the colon equals. The colon equals is a newer notation for this, I believe.
Something that works with computer.
Yeah, it's easier to do that than to put in a LaTeX character for the triple bar. So, okay, so this is that. I'd like to operate on this by next Tuesday, and we'll do some coin flipping then. Okay, with that then, I want to stop share, and I see all of your lovely faces. This is great. And now I will go back and come to think of it, I didn't have to do that. Oh, well, I'll learn. So I'm going to go to the PowerPoint presentation now and begin to go into the lecture component of the way things that work. So we ended up last time with the separability theorem. And the general idea of the separability theorem is that the sum, and I put the integrals here from minus infinity to infinity. The sum is over how many separable images you have. It's the summation of separable images. And if you have the summation of separable images, you can always write that summation of separable images in terms of one-dimensional functions, the product of one-dimensional functions. And the Fourier transform is the exact sum of the product of the one-dimensional functions. And as we saw last time, this was a little confusing the first time you see it. Usually you think if you multiply in the t domain, you convolve in the frequency domain. You don't multiply there, but that multiplication has to be in terms of the same variable. You have to multiply like a x of t1 times a y of t1. There you get a convolution. But if you multiply an x of t1 times a y of t2, that means the function is separable, and it's a different kettle of fish. And so the two-dimensional Fourier transform is equal to, again, the same summation of the products, where the one-dimensional functions can be used here, very, very easily. And we went through some examples of that, and some of those are on your homework. Next thing we're going to do is, okay, I got my slides out of whack here. So here we have something interesting. We know that we have a vector here. We have a vector t, And we're going to ask ourselves, what is x instead of a function of a vector? What if this is multiplied by a matrix? And we know if we multiply a matrix by a vector, we get back a vector, don't we? What does this look like? What does this do to the function when we multiply it by a matrix? The first thing you can see is that it doesn't matter about the origin, because if t is equal to 0, a of t is equal to 0 also, correct? So x of t at 0 is the same as x of at at 0. What does this mean? This means whatever is done with the function, the origin is thumbtacked down. The origin doesn't move. Everything is with respect to the origin, because the origin is the same before multiplying by the A matrix and after multiplying by the A matrix, because in both cases, if we put the origin in there, we get the same number. So the value at the origin is thumbtacked down, and everything happens at, everything stays the same at the origin. As I believe I mentioned last time, what happens, this is the way to geometrically think about it. When you multiply by a matrix A, depending on what A is, it's kind of like the function is on a rubber sheet. And with this rubber sheet, you begin to stretch it. You can stretch it in one dimension. You can stretch it in another dimension. You can rotate it. And in all the cases, the value at the origin stays the same. So it's always pivoting around the origin. And you can also transpose it. You can take a function, and if you choose A correctly, you can do the transpose of the function also. And we will look at examples of that. So there's also the transposition. So that's the reason we say that there's rotation here. There's scaling, such as just stretching out, magnification, if you will. And then there's transposition. Transposition is when you swap axes, like you flip the T1 axis to be the minus T1 axis. Just like transposition is in one dimension. You have a one-dimensional function as transpose is taking the value in one dimension and flipping it to negative time. I get confused here because I'm seeing a mirror image of myself, okay? And what I'm trying to do is I'm trying to do my hand motions in accordance to the way that you would see it. But then I see myself, but I'm not flipped. And so I'm not sure what I'm doing. It's it's a little bit confusing. So let's take a look at this, and let's dig a little bit deeper into what happens when you multiply this x of at. Now notice this is something we cannot do in one dimension. Well, we can, but it's like x of 3 times t, and we know that that's just scaling, that's just stretching. But notice the rubber band idea still holds here, right? X of t over 3 means you stretch it out by a factor of 3, right? And we can do the same thing in 2 dimensions, except now we have the rotation and we have the transposition also. So let's take a look at an example. Let's take a look at example at the matrix A11, A12, A22, well, you can see the matrix. I don't have to read it off for you. But we're going to multiply this by the matrix. Now, let's see what happens. What is, okay, where's my cursor? Where's my cursor? For some reason, and nobody knows, it's changed to red. I got to figure that out someday. This is what it looks like, right? That's the function that we're looking at. But notice this can be written as x of, what happened to my x here? It got overwritten. This is the same thing as x of A11 T1 plus A12 T2, A21 T1 plus A22 T2. So that's the way that we write this out. Why is that? Because this matrix vector multiplication, maybe I should write it out this way. This is equal to x of If we multiply these together, we get what? A11 T1 plus A12 T2 times A21 T1 plus A22 T2, right? So this is our new variable. We can call this tau 1, for example. And this is our new variable here, which we can call tau sub 2. And if we were to write out this vector in longhand, we get this expression that I've written here. Does that make sense? So what is happening here? Well, let's take a look. Before, by the way, everybody knows that if the pictures that you're seeing cover up the screen, you can move the pictures, right? You can click on the mouse and drag the pictures elsewhere. Okay. That means the following mapping occurs, if you will. Okay. Okay, before T1 is equal to a constant, that maps to the line of the new entry for T1, right? This maps to the point A11 T1 plus A12 T2 is equal to a constant. Is that okay? In a similar fashion for T2, the T2 is equal to a constant is now along the line A21 T1, well, you can read it here. That's equal to a constant. So that's the map. Now, this looks like the math. It's better if we can draw a picture. So let me give you a picture here. Here we have just a rectangle function, which is shifted so that the origin is at -1/2, 1/2. And you can see with this rectangle function, we have the axis t is equal to 0. We have the axis T1 is equal to 1, the axis T2 is equal to 1, and the axis T2 is equal to 0. Take a look at that. Does that make sense? Now this is being replaced by, the T1 is being replaced by, if we look here, that's being replaced by A11 T1, the matrix vector multiply, this is equal to 0. Now that's the equation of a line, right? On the T1, T2 plane. That's the equation of a line, if you have the right A11 and A12. In a similar fashion, the this function, T1 is equal to 1, is no longer T1 is equal to 1, but it's equal to this equation is equal to 1, which is also the equation of a line, but the line doesn't go through the origin. And we can see the same thing happens for T2, and T2 is equal to 1 and T2 is equal to 0. We have these axes done. Now, in this example, I'm assuming that the A11s are positive and a bunch of other stuff, but it's supposed to give a generic idea of what is happening. But do you see the idea of the rubberness of it? First of all, the rubber sheet idea. First of all, the origin here is the same as here. Remember we said that after the transformation that the origin is the same? So the origin in both the cases is the same. So that is thumbtacked to the plane, the rubber sheet. And then the rubber sheet, in this case, it kind of looks like it's kind of stretched at a 45-degree angle, right? For this value of A11 and for these values of A, the elements of the big A matrix. And so this is conducive of the idea that we are on a rubber sheet and we are stretching this rubber sheet as we multiply it by A. This works most of the time, not all of the time, but the idea of the rubber sheet is very nice. So I want to get into some specific examples, which I hope will clarify this. let's look at, for example, this function. This function is a picture of a cross. And I think you can see the cross here is here and here. And this is here. And I'm just kind of assuming here that everything in the shaded area is equal to 1. Everything in the non-shaded area is equal to 0. Is that okay? So what we're saying is if we use the same parameters that we did before, the function x of at, the function x of at, by the way, I can't do capital letters when I write, so I usually underline the matrix. Man, shaky city here. It's not letting me erase it for some reason. Oh, you know what? Okay, maybe I'll just do it this way. So if the point is that if this is x, oh, it went back to black. So I think when I'm full screen, it's red. This would be x of t on the left. This would be x of at on the right. And it would be 1 inside the shaded areas and 0 otherwise. Is that okay? So this gives an idea on what happens with the scaling. Let me give you some specific examples. This is still pretty general. Let me give you an example of one of them, transposition. Let's suppose that the matrix A is equal to the matrix which is shown here. So x of at is equal to x big parentheses oops. So this is it in vector form. If we were to spread it out, this is just x of minus t1, t2. And if you begin to look at this, this becomes kind of intuitive. In other words, the t1 axis is flipped, but the t2 axis is not flipped. This is easy to interpret. So therefore, if we have an x of t, which looks like this, what does x of at look like?
It goes from the upper right quadrant to the upper left quadrant.
Yeah, it's the flipping around of this on the t1 axis, right? Whoop. So the t1 axis is flipped, so this turns out to be looking something like this, right? So it's a transposition along the t1 axis. Does that make sense? So this is a simple transposition. And we see that if we have matrices that just have 1s and -1s in the diagonal, we get transposition. What would be the case if we wanted to transpose it in both variables? What would the A matrix be if we wanted to transpose it in both variables?
-1, 0, 0, -1.
Yeah, you see that? If we wanted to transpose it in both directions, this would flip the t1 axis and it would flip the t2 axis at the same time. Okay? So this is transposition. Transposition is matrices full of 1s and -1s, but only on the diagonal. Another example of things on the diagonal is the next example, which is scaling. Let's review in one dimension. If you have an x of t that looks like this, say from -1 to 1, with a height of 1 here at the 0 crossing. What is x of t over 2? Remember, this is not, I don't think it's intuitive, but it means it's magnified or stretched out by a factor of 2. Do you recall that? It's stretched out by a factor of 2. So this thing would go from -1 to 1. No, I'm sorry, go from -2 to 2. But it would still have a value at the origin, which was equal to 1. And that's the value at the origin over here is 1. So therefore, if you divide by something, divide by a variable, you stretch it out. You recall that? So this is the situation we have with the so-called scaling matrix. So look at the scaling matrix. We have x of st is equal to so this is equal to x of what? T1 over M1 and T2 over M2. Correct? And this means what? This means that the function is stretched out by M1 in the T1 direction and stretched out by M2 in the T2 direction. Does that make sense? So if we had something that looked like this, and this was our x of t, if we were to stretch it out, we would multiply by M1 in the T1 domain. So this would go out to M1, and it would multiply by M2 over here. So does that make sense? Where M1 and M2 are the magnification, if you will. Again, we're doing a two-dimensional plot where we're assuming that it's 1 inside the square and 1 inside of this rectangle. So we're assuming that. Now, can M be less than 1? Can the magnification be less than 1? Sure, if the magnification is a half, what does that mean? It means that it stretches and it goes down to a half. Believe it or not, I had a court battle about this. Do you want to hear the court battle? It turns out before a patent hearing that you have something called a Markman hearing. And the Markman hearing takes all of the definitions in the patents and gets them out of the way so that there's not arguing about the definitions in the patent litigation. So the Markman hearing, one of the things was that magnification was used in a patent description. And it turns out that, hold on one second. It turns out that, it turns out that I was saying that magnification could be less than 1, demagnifying, because you get into a lot of ambiguous situations. If you have a telescope and you look at Jupiter, are you magnifying Jupiter with your telescope so you can see it? Doesn't a telescope magnify?
It magnifies what you see, but it's still a lot smaller than Jupiter.
It's a lot smaller than Jupiter, so there's an ambiguity there, isn't it? Yeah, your image is still a lot smaller than Jupiter, so you've demagnified. So anyway, that was the thing. The other side was saying, no, magnification was always positive. When you magnified, you made something bigger. And in the common use of the word magnification means you make things bigger. And the judge, who probably didn't do well in Algebra 1, had to decide between these two definitions. And this was a judge in federal court. It turns out that all of patent litigation occurs in federal court. And I was an expert witness, and I brought in a bunch of papers, including my master's thesis, where I used m is less than 1. And then the opposite the opposite side says, no, we must construe this to mean that the magnification is greater than 1. If you look at patent litigation and you look at these Markman hearings, it's all going back and forth and having irritating debates about the meaning of words. And so this was the debating of the meaning of the words. So what do you think this judge, who probably did poorly in high school algebra, federal judge appointed by a US president, I was the expert witness, and I was on the side that magnification could be smaller or bigger. How do you think he ruled?
I'm guessing he disagreed with you.
Yeah, how did you guess that?
Because you can explain why magnification can be less than 1, but to a normal person, it doesn't.
Yeah. And that was it. And I guess that's kind of if you ever write a patent, you have to remember that. You have to use words that are understandable to the normal population. So yeah, I was ruled against. And magnification, according to this Markman hearing, was always greater than 1. Even though here, it's okay to say that the magnification is less than 1. Is that okay? Okay. That's a little bit of history and the kind of the stupid things that lawyers do. Very good. Now, this is the definition of scaling in 2 dimensions. You can do scaling or magnification in m dimensions. And you should all be familiar with this notation. This is the definition of a matrix, and the matrix is assumed to be 0 everywhere except on the diagonal. And if the diagonal is equal to 1 over the magnifications in each of the dimensions, this means that you are scaling in all of the dimensions. So this is the generalization of that idea to m dimensions. Now we get to rotation. What happens if you take an image like this and you rotate it by an angle of theta? Again, 1 inside the image, 1 inside the image. Both of those boxes are supposed to have the same area, if you will. If you rotate an image by an angle of theta, it's this matrix that you're multiplying by in order to get the function rotated counterclockwise by an angle of theta. I think that you might have seen this elsewhere in other contexts, right? Has anybody seen this before? Okay, yeah, so okay. So it's something which isn't totally new, at least to some of you. So that's the rotation matrix, and the rotation matrix can be used to take a function and rotate it. Let's do a little sanity check. What is R at theta is equal to 90 degrees? I'll check out your trig here. What is that equal to?
Transposition matrix.
Yeah, but what's the elements of the matrix? Yeah, it becomes a transposition matrix.
1, yeah, 1, 0, 0, 1.
So is this it?
Wait. No, it's 0, 1, negative 1, 0.
What is it now?
0, 1, negative 1, 0.
Now, what does this matrix do?
It transposes.
It does transpose, but it's kind of weird because this is a 90-degree rotation, and so we're going to have this. Maybe I should put a little lip on here to remove the symmetry. it turns out that we get this result because this is a 90-degree rotation, right? And here's the little lip. So it's a transposition, but we have switching of axes. The T1 axis becomes the T2 axis, and the T2 axis becomes the T1 axis. Possibly I should do it maybe a little bit more to demonstrate the asymmetry. If this is x of t, then this is the 45-degree or the 90-degree rotation, right? And notice what we've done. We have switched the T1 axis. The T1 axis is now the T2 axis, right? The T1 axis is now the T2 axis, and the T2 axis is now the negative T1 axis, right? So it's kind of a funky transposition, but nevertheless, it's we didn't cover with transposition the idea of changing the axis, changing the axes, but this is indeed what happens here. So we see these rotations, which is good. Here's an interesting aspect, and this is going to become important pretty soon. I'm going to be using a notation. Well, the inverse is equal to the transpose. So let's do the transpose. The transpose is cosine, sine, minus sine, cosine. Is that the transpose? Right? And if we multiply by the original function, which is cosine sine minus sine cosine, what do we get? We get cosine squared. You guys can do this. Cosine squared plus sine squared. What's that equal to? Right? Then we get the cosine sine minus the sine cosine. So that's 0. It's hard to see what happens here, but if you go through the math and you remember the sum of the squares of a cosine and that the cosine squared plus the sine squared is equal to 1. You see that this is indeed equal to its own transpose. This is going to become very important when we look at the Fourier transform of rotated images. Because what we will find out, and this is a little advertisement, if you rotate a function, you rotate its Fourier transform. And it's because of this relationship. Now we will use a notation of R inverse transpose. This is the same as R transpose inverse. And I'll ask you this, is this the same as R inverse transpose? Are those the same? They are.
Oh yeah.
Okay, they are the same. In fact, I might add this to the homework. It's pretty easy to see, but so therefore we can use R inverse transpose without ambiguity because the transposition and the inversion are commutative operators. It doesn't matter which one you do first, you get exactly the same thing. Okay. So that's a cool thing about the rotation. And again, we find this out. Here, visualize this with me, if you will. You have an aperture. Remember we said that the far field in diffraction antenna theory is always the Fourier transform of the aperture? Think of that in terms of physics. It's a two-dimensional Fourier transform. What would happen if you rotated the aperture? Wouldn't you obviously just rotate the far field? Just the physics, just your intuition says you would rotate the far field? yeah, so indeed, that's something that we will show, that if you rotate a function in 2 dimensions, you rotate its 2-dimensional Fourier transform. Okay? Very interesting stuff. I think it's interesting stuff. Now, I'm going to ask you a question and see if you can get this. I don't know why I have this. Why do I have this? I think that's just an extra slide. So I will delete that slide. I want you to look at this. Here's a function x of t. I want to come over here and I want to get a function of x of at. And what I'm going to address here is the sequence of operations. The sequence of operations that need to be done. Now, from getting from here to here, it's clearly I don't know, what are we doing? We're doing two things. We're doing a scaling, right? Because this is no longer a rotated square. It's a diamond. So we have magnified the axes, plus it's rotated. Now, what operations do we use to get from here to here? Do we rotate and scale, or do we scale and rotate? You understand the question? Go ahead.
I think we could go either way. The scaling, the rotation would probably be different depending on which sequence.
Well, here's the problem. There's no way that I can scale this and get a diamond to rotate. Could you tell me I can scale this, pull it this way, and get a function that I rotate and get that diamond? No matter how I scale it, in the T1 and T2 dimensions, I'm still going to have a rectangle, right? There's no way that I can get a diamond by scaling. Do you agree with me? Do you see the geometry? Again, there's no way that I can stretch it out this way and stretch it out this way, which is scaling, and get a diamond that I can rotate. I'm always going to get a rectangle. I'm never going to get a diamond.
All right, yeah, I guess I was thinking about one of the first matrix multiplications we looked at, and I thought of that as just scaling.
Okay. Okay. So we see that this is a function of, we clearly do a magnification. So let's multiply a magnification. Well, first of all, we do a scaling, and then we do a magnification, right? Or no, I'm sorry. What am I doing? Not a scaling. Scaling and magnification are the same thing. We do a rotation followed by a scaling, right? We do a rotation followed by a scaling. So here's my question. Is this function x, and I'm going to violate your intuition here. We've seen that the scaling and the rotation matrix do not commute. They're not the same. Rotation and scaling is not the same thing as scaling and rotation. So is it equal to this, or is it equal to this? Now don't forget, we rotate first and then we scale. So which one is it?
Lower.
Okay, how many think it's the upper one? Nobody cares. Okay. It's actually this one. This is weird because you would expect, and when you look at this, first of all, you would expect, okay, I'm going to rotate, then I'm going to scale, and that's going to give me my total matrix, right? But it isn't that way. It's backwards. It's x of, you first of all do the scaling, and then you do the rotation. So it's the second way of doing it that allows you to get this result. And if you did the alternate way of doing it, you come up with a totally different answer.
Yeah, I would say that it's rather intuitive if you think of it as you start with t, then you rotate it, and then you move right to left, and then you scale it.
You know, hold on. I'm getting a deja vu here, and I'm not sure that I'm right here. No, in fact, this is wrong. I fooled myself. Okay, we'll figure out how I fooled myself, because here is what you have to get. You start out with x of t, and then you rotate it. Is that okay? And we're going to call this w of t, the rotation. Is that okay? Then we're going to scale it. And y of t is equal to w of t scaled, right? This is w of t. So we take w of t and we scale it, correct? And notice this is x of rs t. And even though we scaled first, I'm sorry, we rotated first, the rotation is the last matrix we use. Now let's look at this a little bit more closely, because this is a little bit subtle. We take x of t and we're going to rotate it. Is that okay? And just to be clear, we're going to call this rotated image w of t, so we don't get confused by the r. Is that okay? So then we come over here, and what do we want to do? We want to scale w of t, right? So we want to scale w of t. We want to stretch it out in the t2 dimension, correct? But what does this mean? This means that everywhere there's a t here, we substitute a what? st. Everywhere there's a t, we substitute an st. So the operation is actually backwards than maybe what your intuition says. Because in essence, what we're doing is as follows. We're taking the, no, I guess that doesn't do it. Okay. We're taking the function, and you need to follow along these ideas, because I've relabeled it in the middle as to not confuse us. And I hope that doesn't give more confusion than that you would like. So let me do it again. X of t rotated gives you a w of t, right? And that's the same as x of rt. Now to get from here to here, we want to scale w, correct? We want to magnify w to stretch out in this direction. Is that okay? But notice what that means. That's the same thing as x of rt, except what have we done? Everywhere we have a t here, we need to put a s of t. This t becomes s of t. This t becomes s of t. So we're simply substituting in the s of t here again. And we get the x of rs of t. So this is the result. And it's kind of backwards as to what your intuition says. Anybody have any questions? Or are we too far along to that our minds are no longer working? Okay, well, take a look at this. We'll probably revisit this next time. And the takeaway here is that the operations are kind of opposite the way that you think they should be. Okay? So if there's no question, when we meet on, let's see, when we meet on, today's Thursday, my goodness, where did the week go? When we meet next Tuesday, we'll go over the homework problems that I've given you, that I've also given you hints on. Any questions at all? Okay, thank you all, and enjoy your weekend.
Thank you.
Thank you.
Thank you. You too. See. I think I had a question.
Okay, wait a second, David. I gotta stop the recording here.